Hello, my name is Darren Thomas and I am the Director of Educational Research Techniques. This is Simpler Using Machine Learning Algorithms in R. And so we are finally in Chapter 10. And basically there's going to be one video in this particular chapter, one slightly longer video, and we're going to go over how to assess the performance of a regression model, a model that makes numeric predictions. We already talked about how to do this with the classification algorithm, but now we're going to take a look at how to do this with the regression type models. And there are many different ways that we could do this, but what we did in this particular video was we made two different models, and the difference between the two models was the variables that were used for prediction. Now, this is not the only way that you could assess this. You could use different algorithms that use numeric progression, or et cetera, many different ways. But I just want to give you a simplistic idea of how this works out. Now, there are many different metrics that you can use to try to to assess the quality of your model. So you can look at the R-square, of course, that's the most common one. The root mean square error, the mean absolute error, the correlation. You can look at scatter plots, etc. There's lots of different things, but we're going to look at these four tools here. And then at the very end of the video, what's going to happen here is that we're going to take a look at how to do cross-validation. We have done cross-validation in the past in prior chapters, but I want to try to give you an overview about how this applies to assessing the performance of a model after you're kind of settled on the features and the algorithm you want to use. So without further ado, let's go over to RStudio. So I have my code here. I'm going to be using these three libraries at the top: Caret, ISLR is where my data set comes from, and CorePlot. And so what we're going to do is we are going to use the car seats package. So that's the car seat, and we want to take a quick look at this. And so here are the variables that are available, and we're going to predict sales. This first variable right here, using the other variables in the model, pretty much all of them. Now in line 6 right here, I'm moving faster because now you should be comfortable with these things. In line 6, we have our code here so that we can take a look at the scatter plot. Now this code is a little bit more complicated because I'm convinced that you are a little bit more experienced in how things work. And so what this code is doing here is that, as you know, a correlational matrix can only take numeric data. And so what we have here is that we're using the supply function, SAPLY I guess you can call it, and the function inside is that we're removing any variables that are a factor so that we can get our actual calculation or our actual matrix. So that's what all this code right here is telling you. So when I do all this, I get all of my correlations right here. Nice numbers. And I can just tell from looking at this briefly that there's no major correlations except between price and competitor's price. All these are relatively low, so there's no concerns here. Now in lines 10 through 12, I just set up my train and test set. I've done this before. You've seen this code several times. Don't need to explain that again. Lines 15 and 16, I make up my initial model. Notice how I am using all of my available variables in the model. That's why the dot represents. It saves time. And then we can take a look at the initial printout right here by running line 16, which is the summary. So again, you already are familiar with this. Almost all the variables are significant here except whether or not the place is located in the United States. Education is not significant, so how much education a person has no influence on sales of car seats, and the population has no influence there. Those are the ones that have no influence. But overall, this model is relatively powerful for at least the social sciences, with an R-square of 0.87, which means that 87% of the variance is explained by the variables in the model. So that's looking actually very good. So let's go back here to our code, and we will see what else we can uncover here. All right, here we go. Now we're going to do some data visualization. This is going to be the beginning of kind of assessing the strength of the model. So I use my predict function here. I use the model I just created. I use the test data, and I want the responses. And I'm creating a new object called initial model underscore pred. So I go right over here, press Control Enter, and now I want to plot. So I want to plot the predicted values, for sales versus the actual sales in the test sales set. So we press Control Enter there, and you can see that's a pretty nice straight little line there, nice and clean, not bad. Again, when your R is 0.87, you get those sort of things. Now we can also consider the correlation between these, and you can see the correlation is 0.93. That's almost perfect. A very strong positive relationship between the predicted values and the actual values. Very, very beautiful. So having said that, we can also calculate other metrics. And so what we're doing here in line 24 is that we're taking the difference between the predicted values, predicted minus test cells, and we're going to get the residuals. The residual is always the difference between the predicted values and the actual values, that distance between them. So we do that, and now we can calculate other things like the mean squared error. So again, 1.22, this value is only valuable when it is compared to something else, which we will do in a second. So having said that, we can do the square rooted mean square error. That's another metric where you just square it and you get 1.1. Again, these values are only useful when they're compared to something else. So we've pretty much finished our analysis, an initial analysis of the initial model that we made. We can see that we have a very strong correlation here of 0.93. We have a strong R squared of 0.87. And then these metrics, the mean squared error and the rooted mean squared error, they will be useful as we start to look at our second model. And so for our second model, you can see right here in lines 33, we're not taking all the variables, we're taking some of them. So price of competitors, income, advertising, and age. And so all you do is just run the analysis, not that deep. And so you can see here, here's the results. And already you can see that there's some problems here. So you can see that income is not significant, competitor price is no longer significant, age is significant, advertising is significant. But notice the R squared, 0.16, much lower than the 0.81, 0.87 that we had previously. So remember, the R squared is a measure of the fitness, the goodness of fit of the model, not looking good. And so in lines 37 through 39, I'm repeating what I did with the initial model, except now I'm using the second model to make the predictions and to make the plots. So we do that, we make the plot. You can already see, here's the plot off to your right. Let me make this a little bit bigger. And you can see how things are much more spread out. Just to give you an idea, this is the original plot. You can see everything is much tighter and more compact, beautiful model. But this model, much more chaotic. There's no trend. In other words, what is being predicted and what is actual are just there's an incredible amount of variance. And if you see the correlation here, 0.32. Remember, our other correlation was like 0.91, 0.92. There's a big difference here. And again, it has to do with the quality of the variables that we're putting into the model. Now, in line 42, we did this last time. We're going to calculate the residual. That is the difference between the predicted values and the actual values. So we store that, and then we run our metrics. So 7.9. Now remember, in our first model, this mean square error was 1.2. So there's a big difference there. And then of course for the second one, the second value is 2.81. Our original value was 1.1 for our initial model. So you can see that this model is much, much weaker in terms of its quality and what it's able to do and its predictive value in terms of guessing values for the future. Now, what we're going to do finally to conclude this is we're going to do cross-validation. Cross-validation is where you take out a batch of your data. It could be one sample or it could be a batch, say 50 samples or 100 samples, whatever, and you remove those and you predict with the rest and then you test with the remaining. And so what we're doing here, we're doing K-fold. K-fold is where you fold your data into however many parts. We're going to do 10. So you have 10 folds of the data. And so you train your data on the nine parts of it, and the last part you test it on. And then what happens is that you test it 10 times because every time you remove one fold from the training and say that for testing, and then you take the average of the 10 folds that you tested to try to get an idea of the stability of the model. And so this gives you an idea of how well your model will generalize to other models. So having said that, I will set my seed. I'm going to set up my train control here. This is setting the values that I want to use for my cross validation. So I'm using the method CV, and the numbers is the number of folds right here. And so I say that as an object called CHCK. I'll show you what it has inside. It just has like a list here, nothing that deep, just a bunch of information for a list. All right, now what's happening here at line 53 is we're going to make a model called custom model. We're using the train function. This comes from the Caret package. We're using all of the variables in sales. Our data is trained. The method is LM, that's linear model or linear regression. And our TR control, that's this information we just saved here in line 52. So we do this, whoops, we run it, and then we check the results. And so you can see here, it gives you the information, how many samples are in the model, and then it gives you the folds. So summary of sample size, 270, 270, 269, etc. That's how big each fold was. And so the overall R square was 0.865. That's what happened. And then it even gives you the mean absolute error and the rooted mean squared error as well. And so this value is similar to what we got initially, which I believe was like a 0.82, 82% of the variance was explained. And so since our R square stayed about the same, it helps to strengthen our confidence that the model that we develop will generalize to other data sets. That's kind of one of the primary reasons for doing a cross-validation. And so this kind of concludes the video. We went through a lot of material, but I know you can handle this because we've been doing this for 10 chapters now. So let me back up and kind of go over what we did and make sure things are clear. We started by preparing our data. We've done this before. Then we did our train and test split. We made our initial models here. We've done this before, nothing new there. For the data visualization, we of course made the plots. We've done this in other chapters as well. We calculate the correlations, nothing new here. For the metrics, we did something that's slightly different. We calculated the residual, which is the difference between the predicted values and the actual values. And then we calculated two other metrics, mean squared error and the rooted mean squared error. These values are useful for comparison only. They have no value by themselves. They must be compared to some other model that you develop. From there, we set up our second model, which we deliberately, purposely made weaker by only using some of the variables. And we ran all the tests and everything like the same and all the metrics, and we could clearly see that the model was weaker in terms of the numbers. The mean squared error was higher, the square rooted mean was higher, of course, the correlation was lower, the R square was lower, and these are all indications that the original model was better than the second model. And then lastly, we did cross-validation. Essentially, we took the variables that we used in the initial model, and we wanted to see, okay, if we use this model in a cross-validated situation, it'll give us an idea of how well our model will generalize to other data sets. And you can clearly see right here that the results held. The R square stayed consistent, indicating that this model may generalize well. So I hope this was useful for you as we conclude this journey in trying to understand, how to apply machine learning algorithms using R. So, my name is Darren Thomas. I am the Director of Educational Research Techniques. This is Simpler, using machine learning algorithms in R. Take care.